A graph G consists of V, a non-empty set of vertices or nodes, and E, a set of edges. Each edge has either one or two vertices associated with it, called its endpoints. An edge is said to connect its endpoints. A computer network can be modeled using a graph in which the vertices of the graph represent the data centers and the edges represent communication links. A graph in which no edge connects a vertex to itself and no two different edges connect the same pair of vertices is called a simple graph. However, a computer network may contain multiple links between data centers. To model such networks, we need graphs that have more than one edge connecting the same pair of vertices. Graphs that may have multiple edges connecting the same vertices are called multigraphs. Sometimes a communications link connects a data center with itself, perhaps a feedback loop for diagnostic purposes. To model such networks, we need to include edges that connect a vertex to itself. Such edges are called loops, and sometimes we may even have more than one loop at a vertex. Graphs that may include loops and possibly multiple edges connecting the same pair of vertices or a vertex to itself are sometimes called pseudographs. So far, the graphs we have introduced are undirected graphs. Their edges are also said to be undirected. However, to construct a graph model, we may find it necessary to assign directions to the edges of a graph. For example, in a computer network, some links may operate in only one direction. This may be the case if there is a large amount of traffic sent to some data centers, with little or no traffic going in the opposite direction. To model such a computer network, we use a directed graph. Each edge of a directed graph is associated to an ordered pair. A directed graph consists of a non-empty set of vertices V and a set of directed edges E. Each directed edge is associated with an ordered pair of vertices. The directed edge associated with the ordered pair U, V is said to start at U and end at V. Now we'll introduce some basic terminology. Two vertices in an undirected graph are called adjacent, or neighbors, if they are endpoints of an edge. Such an edge is incident with the vertices. For example, A and C are adjacent, and A is a neighbor of C. The set of all neighbors of a vertex C is called the neighborhood of C. We use N of C to denote the neighborhood of C, which is equal to the set containing A, F, G, and H. The degree of a vertex in an undirected graph is the number of edges incident with it, except that a loop at a vertex contributes twice to the degree of that vertex. The degree of the vertex C is denoted by DEGC, and it is equal to 4. Each edge contributes 2 to the sum of the degrees of the vertices because an edge is incident with exactly 2 possibly equal vertices. This means that the sum of the degrees of the vertices is twice the number of edges. This is called the handshaking theorem because of the analogy between an edge having 2 endpoints and a handshake involving 2 hands. As a consequence, an undirected graph has an even number of vertices of odd degree. Now, let's consider a directed graph. For a directed graph, each edge points away from the initial vertex and points towards the terminal vertex. The end degree of a vertex C is the number of edges with C as their terminal vertex. The out degree of C is the number of edges with C as their initial vertex. Note that a loop at a vertex contributes 1 to both the end degree and the out degree of the vertex. Because each edge has an initial vertex and a terminal vertex, the sum of the end degrees and the sum of the out degrees of all vertices in a directed graph are the same. Both of these sums are the number of edges in the graph. A path in a graph is a sequence of edges that connects a sequence of vertices. If the path starts and ends at the same vertex, then it's called a cycle. A directed graph is strongly connected if there exists a directed path from every vertex to every other vertex. While there exists a path from A to H, there does not exist a path from H to A. Hence, this graph is not strongly connected. However, if this was an undirected graph, then there exists a path between every pair of vertices. Hence, this undirected graph is connected. An Euler path is a path that visits every edge in the graph exactly once. An Euler cycle is an Euler path that starts and ends at the same vertex. This graph does not contain an Euler cycle. A connected, undirected graph has an Euler cycle if and only if every vertex has even degree. Hence, if we remove the 2 diagonal edges, then there exists an Euler cycle. A connected, undirected graph has an Euler path but no Euler cycle if and only if exactly 2 vertices have odd degree. Furthermore, the Euler path must start at one odd degree vertex and end at the other odd degree vertex. If we add back one of the diagonal edges, then we have an Euler path but not an Euler cycle. A Hamiltonian path is a path in a graph that visits each vertex exactly once, and a Hamiltonian cycle is a cycle in a graph that visits each vertex exactly once. This graph contains a Hamiltonian cycle. If we remove any edge from this Hamiltonian cycle, we obtain a Hamiltonian path.